இந்த பக்கம் வாங்க. அனைவருக்கும் இனிய காலை வணக்கம். Very good morning to all. Am I audible? Today is the birth anniversary of Emeritus Scientist Homi Jehangir Bhabha. On this occasion, our Puducherry Council for Science and Technology is organizing a webinar on a tribute to the contribution of Sri Homi Jehangir Bhabha. On behalf of Madam Smita IAS, Director, Secretary, Department of Science, Technology, Environment. I cordially welcome all of you to this today's webinar. I welcome our Senior Scientific Officer, Dr. Saga Alfred, who will be delivering the keynote address of the webinar. I welcome our resource person, Dr. Alok Sharan, Associate Professor, Department of Physics, Puducherry University, and I thank him on behalf of our department for accepting our invitation. Welcome, sir. And I welcome all the participants. I welcome all my colleagues of the department. And I hope this webinar will raise awareness in the minds of the participants about the significant achievements of Dr. Homi Bhabha. And before starting the webinar, I request all the participants to mute their audio and video. Now I request our Senior Scientific Officer to deliver the keynote address. Please.
Good morning to all of you. And it's a great day to remember with. And on this occasion, on behalf of the Secretary and Director of the Department of Science, Technology and Environment, I welcome all the participants who are here today and the resource person.
Sir, you're not audible, sir.
Sorry. And Puducherry Council for Science and Technology is organizing this webinar on the commemorating of the 112th birth anniversary of Sri Homi J. Bhabha. And on this day, we are proud to organize this webinar in remembrance of his achievements, a great Indian nuclear physicist. On the topic, a tribute to the contributions of Sri Homi J. Bhabha. Homi Jehangir Bhabha, known as principal architect of India's nuclear energy program. Born to a rich aristocratic family on 30th of October 1909 in Mumbai, his contributions, achievements, publications are numerous. To say some of the main contributions and achievements, he was key in India's development role going beyond the sphere of atomic energy. And he had established two great research institutions, Tata Institute of Fundamental Research and the Atomic Energy Establishment at Bombay, which was later renamed as Bhabha Atomic Research Center, and we all know it as BARC. And he was the man who played a crucial role in the development of electronics in India. An outstanding scientist and a brilliant engineer. He derived a correct expression for the probability of scattering positrons by electrons, and the process known as Bhabha scattering. And explained the cosmic ray shower formation by the cascade production of gamma rays and positive and negative electron pairs. And he was the first to conclude that observations of the properties of such particles would lead to the straightforward experimental verification of Albert Einstein's theory of relativity. His other interest includes, he was a painter and he was interested in classical music. He was a opera enthusiast, and an amateur botanist. He was conferred with Padma Bhushan Award for his outstanding contributions to nuclear science in the year 1954. And in 55, he was selected as the president of the first international conference on the peaceful uses of atomic energy, which was organized by the United Nations at Geneva. And his life and work was quoted by J.R.D. Tata as follows. He was a scientist, engineer, master builder, and the administrator. Homi was a truly complete man. Only few people in this universe had the distinction of such great characters. And today webinar is organized on this aspect. And we have an Dr. Alok Sharan. Sir is Associate Professor at the Department of Physics, Puducherry University, Puducherry, and he will be delivering lecture on tribute on the contributions of Homi Bhabha. Certainly, this webinar is going to throw more light on the subject and the achievements of a great person and his contributions in the field of nuclear physics. And once again, I thank the Secretary and Director of the Department of Science, Technology and Environment on behalf of the Department and Puducherry Council for Science and Technology for organizing this webinar. And now I hand over the platform to the technical person for his talk. Thank you.
Not the entire screen. Yes, yes, sir. This is you already shared. Shared, yes.
Good morning, all of you. At the outset, I would like to thank the Pondicherry Council of Science and Technology to have me here on this occasion to pay tribute to a man who is an institution in himself, Professor Homi Jehangir Bhabha, whose birth anniversary we are observing today. So it's an honor to talk about his work and try to go back and try to see what are the things which we are all acquainted with his persona. So already part of it has already been talked about by our senior scientific officer Sahaj Alfred. I would like to just elaborate on some of the things which he has mentioned, more from the science perspective. At the outset, I would like to convey to all of you that I am basically a laser physicist. And but we have been following this work of Homi Baba since our undergraduate days. So it's a nice occasion for me, and it's that I got a chance to speak about his work and share with you the things which attracted me the most. So here is our Professor Homi Jehangir Baba. For most of us, the moment you say Bhabha, the first thing that clicks is the screen is not clear. I think screen is not okay. Just,
Next.
no, now it is. Yeah, so sorry, there was some. So the moment we say Bhabha, it is like we know as Bhabha Atomic Research Center, after whom, sorry, then it doesn't display there. So it doesn't move. Yes, sir. Sorry for this disturbance. Yeah, so we are, since we are a generation born after the passing away of Homi Baba, so only through some of his memorial lectures and institutions that we are acquainted with this and familiarized with the works what Homi Baba has contributed. Now, he is a scientist par excellence, as already mentioned. He was a brilliant theoretical physicist whose work was path-breaking in the field of cosmic rays. He was born before the independence India, and even at those days, just around the World War, when he was forced to stay back in the country, he was only thinking about how science can help the country grow and establish as a place of eminence where high quality research, which will be at par with the leading universities like Princeton, Harvard, or MIT. So he has that passion to set up an institute. What he found, I'll just walk through some of his life stories. So about him. So Professor Homi Baba is well known for our nuclear program, and this nuclear program is kind of unique in the world. Unlike most of the nuclear programs around, which centers around the processing of the uranium as the fuel, he came up with a brilliant idea of the nuclear program, which is sustainable in the local conditions. That means he looked at what are the resources India has and how do we go about sustaining a nuclear program which was a source of clean energy with zero carbon emission. So that was a contribution during the Independent Day. As soon as India became independent, the government also took a keen interest in his proposal, and he is rightly called as father of the Indian nuclear program. But prior to that, he has achieved his eminent status because of the discovery of cascade process of cosmic radiations, what is called as point particles, which is also called as Bhabha scattering, and theoretical prediction of muons. So I will just walk through all these 4 bullet points in the next few slides. So as mentioned, he was a nuclear physicist, a founding director of the Tata Institute of Fundamental Research. He established the Atomic Energy Establishment Trombay, which is now called as Bhabha Atomic Research Center. So BARC was purely developed for the purpose of developing nuclear energy, and the fundamental science, which was collaborated through all over the world, was done through the institute called as Tata Institute of Fundamental Research. Already his honors have been discussed. or mentioned. That is, he has awarded the Adams Prize, the Padma Bhushan, and lesser known things is that for the work what he did in cosmic radiation was nominated for the Nobel Prize in 51 and 52 to 56. So, what are the contributions prior to he became the nuclear father of our Indian nuclear program? For his undergraduate, he moved to England, where he was enrolled for a mechanical engineering degree. But soon he discovered that his passion is more toward the physics. There is a very interesting anecdote where he writes to his father that they, let me convey, let us know, recollect that he belongs to a very rich Parsi family from the lineage of Jamshedji Tata. So, and they were looking for their kids to take over their empire. So they wanted him to become a mechanical engineer and take over the Tata Steels. But Homi Bhabha has a different idea. After going to UK for his mechanical engineering degree, he developed interest in physics and he wrote back to his father, please allow me to do physics because that is the passion. And it is not that there are not scientists are not available to pursue this or head your empire. But if someone does the work which is close to his heart, the creativity and productivity naturally comes out. So he was allowed to pursue his ambition of doing theoretical physics, provided he completes the mechanical engineering degree. He did that promptly. After his finishing mechanical engineering, he joined Cavendish Laboratory in Cambridge University for his doctoral studies. And during his doctorate studies under Fowler, he published one paper called as Absorption of Cosmic Radiation. So it is like Millikan has already discovered some experiments that there is some intense shower of cosmic radiation which is coming extraterrestrial in origin. That is, they are coming beyond the atmosphere. And then there are some, through some of the clever experiments, what they did, they also found that there are brilliant light which is being emitted or seen from the upper atmosphere. So what they did was, they tried to calculate what could be the possible reason for this observance of extra particles which is generated in the atmosphere. And then they came up with a theory that cosmic rays, which could be in extraterrestrial origin, which can be sun, center of galaxies, or any other far known other stars, which radiates a highly energetic particle at moving at relativistic speeds, when they bombard on your atmosphere, there is a chance that the lot of activity happens because of this. Like say, if you're talking about an atom, the electrons are ripped apart, then it's an ions are formed, which leads to the ionosphere, which is known. Then the energies at some scales may be so high that you have this electron positron pair created will be recombined. So as this high gamma radiation passes through this kind of a medium, electron positron pairs are created, destroyed simultaneously, and keep getting scattered. So he was one of the first to speculate that and show that the cosmic rays, which are extraterrestrial in origin, is actually responsible for what is called as electron shower, which is nothing but knocking off the electrons from the atoms which is present in the atmosphere in the upper layer of the atmosphere there. And these are being unstable, the particles. So electron positron, if they combine together, they annihilate, because annihilation means, see, electron and positron, they have same mass, they have similar characteristics, except the charges are negative. One is called as particle, the other is anti-particle. If particle and antiparticle combine together, they annihilate and leads to the generation of the energy. So that is called the gamma photon. This is in this figure, you can see an electron, positron coming, electron, and then this gamma photon will just scattered off, and you have this is a positron and electron, the mediates with the gamma photon there, and that is gets scattered off. So this process keeps on happening simultaneously. So what they did was they tried to calculate what is the probability of this event being occurring with some heuristic model, and was able to explain that how this electron shower can be generated. And that was the first paper, which was called as absorption of cosmic radiation. Subsequently, he went on to collaborate with Niels Bohr at Copenhagen after getting his first studentship, which is, I think, if I remember right, it was an Isaac Newton studentship he got after the publication of the first paper. And then he carried on more work on the same lines and tried to do some quantum mechanical calculations where he actually calculated the exact cross section. Now, when you say about cross section of this positron electron scattering, what does it mean? Cross section is something, if you take any material, whatever shape, what we do is that you take a knife and cut it along plane, let it parallel. So the area exposed is called as cross section. So how is it the same thing as what we know in our home? Here it is slightly different meaning, in the sense that, let's say if I have a two particle, like a classical particle, which comes head on. Okay, they come, like if there are two finite particle of finite size, when they come head on, what is the cross section with which they can hit each other? It will be the size of double the size of their dimension, which each one sees as a projection. So this has some diameter d, this has some another diameter d. So as a result, if they come head-on collision, the cross section is d. The maximum with which it can collide is 2d. Okay, so as a result, there's a glancing angle. This is assuming that each of these particle doesn't exert any force on the other. Okay, but what happens in reality, not only this particle has some mass, but it has some other properties. It can be charged particle, it can be magnetic charge or electronic charge. And as a result, it has a certain field around it, which the other particle will simultaneously feel. So as a result, even if it, let's say, is a positive charge, what is the tendency? It will come and try to deflect. If it is positive negative charge, they will come and try to annihilate. So when we say the cross section, we say what is the probability with which these two events is likely going to occur. The higher the cross section, more likely that event is going to occur. And that is what this cross section. So once we know what is the source of radiation, or let's say, if I can measure what is the electronic shower now, because I can have the luminosity here. Okay, by some, you might have in some of the MSCA experiments, you have this Geiger-Müller counter where you actually measure the cosmic ray radiation, which is, and try to draw a histogram on that. So that is nothing but there's some charged particle which is simultaneously clicking inside that vacuum tube. Cosmic rays are getting bombarded. That GM counter is not measuring any event which is present in the lab. Your lab is continuously bombarded with some cosmic ray radiation which is penetrating all through your buildings and other things and passing through you as well as that instrument, and that is where it registers the click. We are talking about the same cosmic ray here. So this, now what we do, I want to measure this. So what I do is I try to measure across this entire, let's say, sample area on the screen there, where I do a sampling on the sky and try to measure how much of the electron detection can be there. Because there is no reason why the atmosphere should rip apart the atoms. Okay, so the only way it can happen is with the presence of cosmic ray. If I know how much of the electron are present or measured, then what is the probability that how much of this was bombarded by what is the amount of cosmic rays were present which induces this particle? Because let's say I am bombarding with 10 gamma photons of extremely high energy. So are those 10 gamma photons will be responsible to convert generate my 10 electron positron pair? The answer is no. We talk always in quantum mechanics what is called as probabilities. Among the 10 photons, is the likelihood of probability is that among the 10, if it is 1/10 or 0.1 probability, then 1 in the 10 photons will initiate electron positron pair. So as a result, what we expect is, so if I measure 1 electron on my terrestrial surface, I know that 10 gamma photons would have come. This calculation of this ratio is very important unless until you know what is the cross section, which is nothing but a representative of the probability of that event to occur. Then I can know what is the value of the gamma ray bombardment. So this is how the importance. So now we have since the theory was proposed and observations were done, and then based on whatever the known source of cosmic ray radiation, there was a prediction, like if you talk about, let's say, sun as a primary source of a cosmic ray radiation, we know that sun is powered by a nuclear fusion where hydrogen gets constantly getting converted into helium, and then there are a lot of bombardment of different particles are getting ejected, the magnetic field surrounding it, because of the constant charge, because sun is kind of in the plasma state, ions are created, so there's all ripped apart. Some traces of higher elements are also present on the sun. Those are all sprue in the entire solar system, and some of them passes through the earth. So this is, so I know now, looking at the size of the sun, I know what the reactions are happening there. I can find out what could be the possible number of, nuclear physics tells me that how much energy is related when two hydrogen nucleus combine to generate a helium neon. So from the estimate of that energy released, we can measure the intensity of the light of the sun. So from that, I can calculate, measure the entire spectrum, so I can try to get a total luminosity here. And then from this model where I've constructed about explaining the nuclear cycle which is happening in the sun, I can have a broad estimate as to how these high energetic particles can be emitted. So this measurement of the electron shower on this can help me directly correlate what could be, if assuming sun is the only my cosmic ray source, then what could be the likelihood of that event. So that you cannot predict unless until you know this, the conversion factor which is given by this cross section. And that lies the beauty of his calculations. It was a tough task, but the theory was accurate to predict this. And nowadays in the linear accelerator collider, where these electron positrons are generated frequently, we expect to see, measure this shower and to measure the luminosity of this scattering based on this, what is called Bhabha scattering. The name to honor the electron positron scattering is called as Bhabha scattering to honor his contribution in this field. It is a very path-breaking field, which helped us see the why it is path-breaking. Not only explains one phenomena, but it helps us to understand much more physics and give a deeper insight into what is happening, as if you know this quantity, what all things you can understand from that theory. So that is what was proposed by him, and that was one of the principal theory where he shot into eminence and he was appreciated and accepted as a stalwart in this cosmic ray, a doyen of this theory. And based on when he carried on the theory further, he observed certain kind of a behavior in the atmospheric particle that some of the energies were not being agreed with this thing. He's predicted one particle, which we now call it as muons, having similar properties like electron, but almost 200 times the mass of the electron itself. And that could be the responsible one for the interaction what we see in the cosmic shower. So I'll just show that slide. So this is the growth of a shower. So you can see that one particle is coming, knocking off, then it leads to another cascading effect. Not only it is interacting at only one level, that one photon is being responsible for electron photon, then it is subsequently, because what is happening, you are separating from the vacuum, you are knocking off the electron, then you are ejecting it. It is creating electron-positron pair because of the presence of this photon. Then these things recombine somewhere, again a photon is generated with equal energy, and then it is again leading to another scattering of electron and positron. So this kind of works as a cascading effect, and each one has certain probabilities, and that is what is being predicted by his theory. So this thing, and also the production of what is called a secondary cosmic ray particles, was what was being understood by the prediction. I mean, through this he predicted the presence of muons, which he called the vector mesons, had a spin 1 and odd parity, same thing like what electron, and he could explain that this fact explained that there is an existence of a triplet set of a deuteron, which is used in the isotope version of hydrogen, which is used to produce heavy water, and that is in the one of the lowest stable state. So you see, so sometimes this sorry. So now these particles, called whatever this quasi particle, has certain half-life. That is, they are not stable for a long time. So what does this, what we say normally, that in the literature of nuclear physics, that every particle has its own half-life. Probably you would have encountered this half-life in terms of your nuclear physics course, where radioactive life has radioactive decay has certain lifetime. So it decays with certain amount of years. It can be millions of years or something. Okay, so in that, while what does that mean is that such materials which are unstable in the period of 1 by tau, the fraction of that much energy. So if I start with 100 particles, and let's say if it has a lifetime of 1 hour. So what I expect, after 1 hour, the number of particles available to me will be reduced from 100 to 1 by E of the value. That is 1 by 2.7 factor. So that is almost like 40 number of particles around that will be seen. So, and that ratio keeps progressively decaying. So during that passage of time, so we try to calculate how much distance it can be traveling. So within that lifetime. And for this, the experiments were done in polar gold field, which matched with the theory. And they predicted that since these are all relativistic particles, so it has, and that is where because mesons are supposed to be relativistic particles, can travel at the speed close to the speed of light. So as a result, you experience time dilation. So you experience the distance which actually travels will be much different than what is theoretically predicted. So if you are able to measure this time difference, what is supposed to be in the ideal condition, the lifetime, and what is the other speed where it is trying to slow down, you will be able to measure this time dilation, which is a prediction of Einstein's special theory of relativity. And that's what in his one of the contributions, what he was mentioned, that his theory actually explained the observation of such particles, which straightforward experimental verification of Einstein's theory of relativity. It is the time dilation effect which was observed in the passage of mesons to the Earth's crust. And most of these experiments are done deep down the Earth. In India, most of these experiments was done in polar gold fields, where TIFR has a laboratory. So these are some of the important scientific contributions which threw him into the limelight, and he was considered the doyen of the cosmic ray. And it just so happened, as he was pursuing his research area, he came back to India for a trip, and the World War broke. And fortunately for us, he decided that he will stay back to the country. The first job he took was in Indian Institute of Science, which was director. That time the director was our Sir C.V. Raman. He was appointed as a reader, and he was asked to start a cosmic ray laboratory. He soon realized the experimental skills and the staff required to do it cannot be done. These studies cannot be done in isolation by one individual scientist. You require a pool of people who are dedicated only for one purpose. So therein he proposed to start this, what is called as Tata Institute of Fundamental Research. He wrote a proposal to J.R.D. Tata, where he has a nice anecdote which was already mentioned by our scientific officer, that how J.R.D. Tata, the Tata group was, not J.R.D., I mean his father was convinced, Jamshed Tata, that funding should be given to start an institute to just cater to the needs of understanding fundamental science. And his idea was, since he was from cosmic ray, so let us do theoretical physics dealing with cosmic ray, nuclear science, and mathematical physics. So that is how this birth of TIFR started. And after, during the independent India, he had a chance. His stature was already been established as one of a very promising scientist of great pedigree. So, and his closeness with our Prime Minister Jawaharlal Nehru ensured that he has always been in the scheme of things with our government of India. And it's not a surprise that we can see that it is during that generation or that period, we have some eminent scientists who are institutional in themselves, like Vikram Sarabhai, Meghnad Saha. They are all able administrator, scientists, brilliant scientists, each one heading each separate complete profile, which has put India on a firm scientific background to take us to the next century. So all that, so you can see that our Pandit Jawaharlal Nehru, the Prime Minister of India, was surrounded by brilliant scientists who were willing to take up the responsibility of administrator. Meghnad Saha was also a member of parliament. These were the advisors to him. Vikram Sarabhai, who started the Space Research Organization later on. And of course, when the BARC was started, TIFR was started, Homi Bhabha has taken a couple of students, Singhvi and Harish Chandra, a mathematician, to start the theoretical physics division. Harish Chandra Institute of Mathematical Sciences is named after Harish Chandra, who was a student of Homi Bhabha at Allahabad. It's one of the premier institute of mathematical sciences. So he's starting. What they envisaged was that this is much before the active program of Homi nuclear program was started. Homi proposed this idea, apart from starting the Tata Institute of Fundamental, that India's energy demand can be met if we go nuclear. Nuclear not for the weapons, because already we have seen the devastating effect of the nuclear weapons in the bombing of twin cities of Hiroshima and Nagasaki in Japan in the Second World War. So what he was proposed was nuclear energy for peaceful purpose, which he was also the president for some time. He came, as I mentioned in the initial, that he came up with a unique program for India. What is the uniqueness of a program? The outside nuclear reactors are based on the fuel, which is a fissile material, which is uranium 235. India doesn't have that kind of a uranium reserves, but it has plenty of thorium reserves, which is a low yield, but it's not a fissile kind of thing, so it has to be upgraded. So the cycle which was implemented in 3 stages. Keeping in mind the available resources, because everyone knows that once it comes to fueling your own reactors, catering to your own energy requirements, because these are all limited resources, though non-renewable, but definitely clean and cheap with zero carbon footprint. So as a result, they came up with a 3-stage reactor, keeping thorium in mind, which is plentiful available. India has one of the largest resources of that thorium around the whole world, whereas uranium is very, very minimal. So they started with the program with whatever the natural uranium fueled with heavy water reactors, and then plutonium filled fast breeder reactors, which will generate in return more of the thorium, which will feed into the 3rd stage of our reactors. And this is supposed to last for almost 3 to 4 centuries to meet most of our energy requirements. So that is the grand plan which they Bhabha proposed, and it was immediately accepted. Apsara was demonstrated in BARC. Tarapur reactor was started under this, and this is that 3-stage reactor which was being proposed, and this is some predicted numbers by which how much energy we can expect. The advantage of using nuclear reactors is one thing, that these nuclear fuels are extremely compact, high density, and for that density it can generate megawatts of energy. If I have to do set up a corresponding thermal power station, the amount of coal or the fossil reserves required will be humongous. It will immediately deplete whatever the India has, the natural resources. So that is why the other source of energies are your hydroelectric dams. Of course, thermal power station was initially the first one to start, then followed by hydroelectric projects. And we know how devastating the hydroelectric project has on the environmental impact. Though it's a clean source, but the environmental impacts are huge. And then, plus, it has a shorter lifetime because of siltation and other problems. Thermal power plants produce excessive soot, larger carbon footprints, easily available resources, cheap for the now, but long-term impacts are huge because it pollutes your environment, also contributing to the greenhouse effect, which all the climate changes what we are seeing today are these are called a greenhouse effect, which is combined due to the movement of pollution because of our transport vehicles as well as thermal power plants. So this proposal of nuclear energy, which only requires at the building stage some carbon footprints are there, but otherwise once the energy is generated, it hardly has any. So it was started with a natural uranium, whatever we have, put under pressurized heavy water reactor, which will generate some energy, which was predicted to produce 10 gigawatt for 40 years at 0.8 capacity factor, and in generate will release or make depleted uranium, which will convert to 238 isotope, and plutonium can be used as a mixture with this natural uranium, and that will be used as a feeder to the what is called the fast breeder reactors, that is this plutonium uranium mix in the stage 2 along with some thorium, and that is supposed to generate about 500 gigawatt for about 100 years at 0.8 capacity. So whatever I have taken most of this things from the internet resources, where I have always given the link as I'm explaining through the slides. So after this conversion, whatever the 233, remember this is not a fissile material, I mean not for the weapons grade material. So this, whatever is being created, which is going to be used to fuel the third generation of our reactors, or third stage, which is for with the mix of thorium. So thorium is generated as a byproduct and it can sustain it itself for another 350 years with 500 gigawatt of capacity. Of course, we have not been able to achieve this, whatever the grand plan, but nevertheless, the efforts are on, the reactors are kept, and so this is what I was saying about stage 1. We have pressurized heavy water reactor where uranium is converted into plutonium and it generates heat, which is used to convert energy. So the uranium is getting converted into the concentration of uranium isotope 235. Uranium 235 is not required. So uranium isotope of 238 can be directly used to the reactor core. And heavy water, which is the deuterium oxide, which is what I just mentioned, is a stable isotope of deuteron. So hydrogen in the isotopic form of deuteron is used. So DTO, this is a water, heavy water, because instead of hydrogen, we use deuteron as the nucleus of this thing, molecule, which is created for why it is used as a moderator, because of its latent heat capacity is much larger compared to the normal light water reactor, and therefore it is used as a coolant to absorb most of the heat in this pressurized high water reactor. So pressurized high water reactor was natural choice for implementing the first stage because it had the most efficient reactor design in terms of uranium utilization. So generating this, you have created a plutonium which is going to be used for the next fast breeder reactors, and that is where this fast breeder reactors, plutonium 239 undergoes a fission to produce energy, which produces more energy, and the uranium 238 present in the fuel transmutes to produce additional plutonium 239. So you can see that one feeds into the other, and that is why it is called as fast breeder reactor. So what does that mean is essentially that fuel is being pumped into this reactor to generate more fuel, which will feed into it, and some of it is created as a byproduct, which will be used to feed the third stage of the reactors. So thereby you are constantly increasing the enhancing the capacity of power generation. Remember, these are all fission-based reactors. It's not a fusion, which is the holy grail. Okay, so like it is like talking, the equivalent term is, this is like a controlled atomic bomb. That is what we can talk. The fission, nuclear fission is like what happens in your atomic bomb explosion. Fusion is the reaction which is responsible to drive the energy from the sun or the stars, or which also is responsible for the detonating of hydrogen bomb. So that is because of the fusing of two hydrogen nuclei. So that requires a tremendous amount of energy. But that energy, when is used to utilize fused two nuclei, will generate much more energy than what is actually utilizing to create it. So therefore, a lot of research. Recently, there was some Chinese newspaper reports where last year they have actually created energy out of this fusion reaction, and they have successfully, and they are on the lab scale. In India also, we have an institute called Institute of Plasma Research, where this active research is going on to generate energy from the fusion reaction. But so far, it is not in the commercial scale. So research is going on in that aspect. So this was the grandiose plan, which was successful. And this at stage 3, whatever we have generated, the additional nuclear fuel from the previous 2 stages is used in the stage 3, and that is where the life of our nuclear reactors is going to continue for more than 350 to 400 years with almost 500 gigawatts. We are nowhere close to the predicted numbers, but nevertheless, the activity is very, very important. The fact is that This was thought about as a long-term plan by Professor Homi Bhabha in the year 40s and 50s. And our entire nuclear program is based on this. So we have proliferation of Bhabha Atomic Research Centers, atomic research centers spread around country for specific purpose based on that grand plan towards achieving nuclear energy, to have clean source of energy from nuclear reactors. Of course, nowadays hydrogen fuel is being most talked about, where you can have, but that is mostly for transportation purpose. On the mass scale, still nuclear energy is one of the source, active source. So, what is the advantage? It is a low cost energy. It's a reliable power source because it doesn't depend on any seasonal fluctuations. Once you put amount of thing, the particular concentration of your nuclear fuel, you start generating. Of course, assuming that they have achieved criticality. So there's some minimum number of atoms or material required to generate this energy. Okay. So and that is it has to be as you know that it generates too much of energy, and small mistake, that means you have an atom bomb sitting at your doorstep. So it is an extremely complex, tedious process to have a controlled fission reaction to generate energy. So a lot of care is there in commissioning it, but once it is, you have a control over it, that's one of the best generation of power. Okay, so and it is sustainable over a long period of time. It has zero carbon emission, and this is a high energy density which I was talking about. So it doesn't require much space to generate per gigawatt of energy. Disadvantage, environmental impact is basically your accidents, radioactive decay are the one of the other problems which can fuel it. The other problem is the water. It requires a lot of water to cool the heat generated. So thereby, most of these nuclear reactors are situated in and around your water bodies, basically to the either the seashore or some river source where plentiful water is available around the year. And what happens is, because of water being sucked in, used for cooling the reactors, and then again thrown out, the water temperature increases, and as a result, the aquatic life starts changing, and that has an additional water environmental impact. So that becomes, say, like you are disturbing your ecosystem. So that is one more other thing. And of course, Chernobyl and Fukushima reactor, which was I forgot, I'm not able to pronounce the name of the Japanese nuclear disaster, but Chernobyl in Russia was well known, and accident, a lot of people lost life. Then what to do after this? So this is a non-renewable energy resource. Once the cycle is wasted, it is converted. What to do with that radioactive waste? So that is a management of radioactive waste is always a serious challenge, where people have to still find a proper answer. Right now, they keep on dumping it in some deep point in the oceans there. So that was the grandest plan with which he has contributed, and he has helped India develop to achieve whatever. It is not that the generation of the nuclear energy which is being important, but what Homi Bhabha has brought in is the thought how science can be used for the developing a nation. He, along with his team of other high-profile scientists, showed that yes, we can do it. He was one of the first person to initiate this kind of a science to the service of nation. Not only he was a brilliant scientist, but he foresaw, managed people, managed establishments like BRC. They are a humongous big organization which he could manage and see how it can be done. Of course, he was also asked to be director of the nuclear weapons program at that early time. But I don't know much about this. The details of that is not available. But he was always a peaceful votary. I mean, he was always for peaceful use of the nuclear weapons, nuclear energy, for which he was nominated as the president of the United Nations. Apart from that, we have a great institute like Tata Institute of Fundamental Research, which is primarily focused on natural sciences, mathematical, biological science, and theoretical computer science. The ambience with which he brought in reflects the approach with which Homi Bhabha actually believed in. if anyone gets a chance to visit TIFR, it will reflect what kind of persona he is, the chance where painting, music, auditorium is created there, where you can spend times in the evening or different programs, the layout of your the reception area with a lot of artistic artifacts which welcomes you. The ambience created is just mesmerizing, and it provides a pure platform for all the great scientists which TFR has been producing over the years. Majority of Bhatnagar awardees are from that. Scientists of international repute keep visiting, and that is, it has really actually nucleated great science research in the country. And it was no surprise that the India's first digital computer was also built in TIFR. To its credit, TIFR, because of its outreach, as it grew, it has created institute all over India of repute in different fields. Of course, it has that is National Center for Biological Sciences in Bangalore, National Center for Radio Astrophysics, which was also called as Giant Meter Wave Radio Telescope, which is situated at Pune. Then National Balloon Facility at Hyderabad, which is used for cosmic ray, so what is called balloon sounding. Then applicable mathematics at Bangalore. Then now to expand on their academic activities, TFR Hyderabad has been recently launched in the last 5 or 10 years. So it has, the campus is now functioning. And to complete its outreach program, they have also launched what is called Center for Science Education, which keeps on devising innovative ways about bringing science to the doorsteps of the not so privileged students, as well as emphasizing about what all things can be done. So this is an example of a photograph of the big telescope, which is Giant Meter Wave Radio Telescope, which is supposed to probe the existence of the 21 centimeter hydrogen line, which is supposed to be existed during the Big Bang time. And 32 of this array antenna. This is like something 20 to 30. It's a tens of meters in diameter. And this design is something unique to our NCRA. Normally you'll have a complete parabolic, but they have come up with this wire mesh structure, which effectively works as the same way as what the normal parabolic dish would have been working. This is for cost cutting without losing the efficiency. Also, that puts, since the weight is less, it is easily steerable, and it has some several discoveries which have been contributed to this thing. So Professor Govind Swarup was the founding director of this center. Siddiqui was started the biological sciences. So we have a lot of luminaries which he was brought. And as mentioned, J.R.D. Tata about how it paid his tribute to the Bhabha's extraordinary vision was Homi Bhabha was one who made me believe that some men in human history are born with a stamp of predestination on them, which leads them to accomplishment beyond ordinary human capabilities. Some of them, and Homi, alas, was one, are also predestined to die young, and unconscious premonition which drives them to superhuman effort to complete their task in the short time allowed to them. Remember, he died very young at the age of 56 in an aircraft accident, which is still a mystery, but it's been accepted that there was some error with the communication with the airport and the pilot. So within his 2 decades of being present in the India from 39 to 56, Bhabha has transformed the scientific landscape of the nation. His leadership had inspired generations of scientists and engineers who worked with him at TFR and Atomic Energy Establishment. And soon they too also had embraced his vision of a new India, developing a new sense of optimism and confidence in their abilities that had never been seen in the country before. We have Raja Ramanna, we have M.G.K. Menon, Sarabhai, Harishchandra. So to name a few, these are all the stalwarts which was thanks to the institution which Homi Bhabha provided or the platform. So it actually completely acted as a figure. So if time permits, can I talk about the laser group or should I finish? Huh? Yes. Okay. So here, since I'm a laser physicist, I thought that I will just talk about what is the work which we do at Puducherry University here using lasers. So lasers, as you know, are a monochromatic source of light, high degree of purity. They're intense, coherent. That means you can focus them to extremely small spot because of its narrow divergence, and they can travel long distance without being affected by the atmosphere. Of course, barring the scattering. So its pure properties are actually finding multiple of uses. I'll just showcase 4 slides where the research which we do in our lab. One is use this intense source of light to generate a new source of light, which is second harmonic generation. That is conversion of fundamental wave into second harmonic. Then use nonlinear optical technique, which is called as electro-optic, to make scanners, which is nowadays used. Then use third order nonlinear optical properties to probe and manipulate optical material property. And for medicine purpose, we use lasers for what is called as antimicrobial photodynamic therapy. And we are in the process of establishing quantum lab, quantum system lab, where we are going to generate entangled photons for quantum interpretation processing. So what we do, we have a femtosecond laser. Femtosecond means the pulses which are generated from these laser sources are extremely tiny, to the order of 10 to minus 15 seconds, hundreds of femtoseconds, and they are of particular frequency which is sent through some material which you would like to study, and then you try to have an analysis. So this material, depending upon the structure, will generate second harmonic, which is 2 omega. So that is how. So let's say if I'm using an Nd:YAG laser with 1064 nanometers, I can generate 532 nanometer output. So I have converted into second order. So that is how we can generate the second or change the color. So this is for using for probing some fundamental science, but also it finds place in the display technologies also. Here what we do is we modify the optical material properties of the material, which is called as ferroelectric here, to create some domains, up and down switching, apply electric field and reverse the direction. And then what we do is we can pattern this to create lens stack of lenses. Remember, this is situated in the entire 25 paisa coin. You may not have, some of you may not have seen 25 paisa, but it is almost like 2/3 the size of 50 paisa 1 rupee coin, the new one which you are seeing. So these are stack of lenses. So if I can change this electric field, I can change the collimating properties of this beam. So this is used for the integrated optics application. And the principle here is, like in the normal lens, what we do is the refractive index is constant, but the radius of curvature is different, and thereby you have lens of different focal length. But in this particular example, radius of curvature is fixed, and applying electric field, I manipulate the refractive index, thereby changing the focus of this lens. So I don't have to physically change the lens itself. I just apply field, and thereby the refractive index changes, and therefore the focusing property changes. I can create what is called focal lenses. So I can create the scanners like this that allow this field. Instead of going here, it can deviate depending upon how much electric field I am applying from the bottom and the top electrode. So this angle can be controlled, and I can route it, back it in, and it is used for the new version of the electric optic scanner. In traditional department stores, if you go and look at the scanners which read the barcode, it is based on polygon. The laser shines on the polygon and then just scans quickly. It involves, for high-speed purpose, it is not useful because you cannot go more than hundreds of hertz. But these scanners can go into megahertz, so thereby increase the speeds. We used to probe the material property, and we have shown how lasers can be useful to study some basic material properties or sciences, where phase transition, that is one state of the material to the other state as you increase the temperature, can be easily measured or probed by what is called as second harmonic generation. And then the other important application which we recently are pursuing is use in the what is called antimicrobial photodynamic therapy. So what we are trying to do, we have some growth of some bacterial films on certain cells. Let's say you have an urinary tract infection, then we want to kill those bacteria by sensitizing the dye. So we spread the dye on it and then shine the light on this so that they become inactivated. And that is what you can see from this color of the confocal microscope. That so these are the different bacteria in the A and these are B. A is aeruginous and A is aureus. A and E are comprising non-irradiated and irradiated films. These are non-irradiated and irradiated. That means I have exposed these films here. A and E, sorry. This one. This is illuminated. This one is non-illuminated. Okay. Are so treated, and F and G comprise of the with now we have modified with what are the functional elements of carbon nanotubes and some dyes, malachite green along with carbon nanotube, which you dope it and then send it, and then we can see that activity is reduced in this, and that is proposed as one of the part photodynamic therapy. And this is what I was saying, that in the second harmonic generation, if I generate two sources of light, I'll see a two-ring kind of structure under what is called a spontaneous parametric down conversion in a material called a bibliocrystal, and these two intersecting points produce a kind of a light which is very, very interesting property, which we call as an entangled photon, and this is the source of quantum computing power, which is now the bedrock of most of the quantum technologies. So this and more, and I think most of you are familiar with different applications of laser technology in basic sciences or laser technology in the industries, defense, nuclear energy, which is here, it is used for isotope separation as well as for creating nuclear fusion also. We use lasers. So these things are taken from the scientific world and the medical field also. So with this, I would like to thank you, and
Thank you.
Questions. I can stop the presentation.
Thank you very much, Dr. Alok Sharan, sir, for your highly technical and lucid presentation on the countries. So any questions, please ask Alok, sir. So I think we don't have any clarifications, such that the presentation is very understanding to everybody. Once again, thank you, sir. Now it's time for a vote of thanks. I request my colleague, Mr. Shivakumar, to extend the vote of thanks.
Thank you, sir. Today we are celebrating 112th birth anniversary of great Indian nuclear physicist Homi J. Bhabha. On behalf of our secretary cum chairperson, I thank our resource person, Dr. Alok Sharan, Associate Professor, Department of Physics, Puducherry University, for delivering a wonderful lecture on this birth anniversary. We learnt a lot, sir, about the cosmic shower, time dilation of muon, and the experiment done at the Kola Goldfield, and also about laser physics. I would like to thank our senior scientific officer and scientific officer who are behind the webinar for making it great success. I would like to thank all participants for being here today and listening the whole session of the webinar, and hope this webinar is useful to all participants to know about Homi J. Bhabha and advancement in nuclear physics. Further, I kindly request all participants to fill the feedback form to give e-certificate, for getting e-certificate. Thank you.
Thank you for having me. If you have any questions, I am available at Puducherry University Department of Physics. You can check my email address. I'll be available. Thank you once again.